However, you're getting another assignment tomorrow. So between today and tomorrow, both assignments are due on Friday. So tonight, like you'll be able to do, I'd say, up until probably, I don't know, 39-ish. And then after that, maybe like once it starts with the graphs and the graphs get pretty involved, maybe you want to just stop at that point. But you will have like another assignment tomorrow that's a worksheet on top of that. And both of them will be due on Friday, and I'm going to be collecting both of those assignments. So just again, like it's Tuesday's assignment listed on the assignment sheet. And then tomorrow we'll have a worksheet. Friday we're reviewing for your quiz on Tuesday of next week. Okay, so if you invest $1 at an annual interest rate of 100% for a year, how much money do you have after the year? Luke, how much money do you have? $2. Because you've earned 100% of that dollar, so you currently have one, you get another $1 at the end of the year. So that's $2. The next one says if you invest $1 semi-annually with the interest rate of 50% for 1 year. So that means like in July, I have $1, but I'm going to get an extra 50% on that dollar. So how much money do we then have in July, halfway through the year? $1.50. Because you're getting 50% of that dollar being added on, so you get like 50 cents. So now I have $1.50. At the end of the year, I get interest on that amount. That's what like compounding interest does. So now I have $1.50. How much money then would I earn at the end of the year? Why $2.25, Brandon?
Because half of 150 is 65.
Right. So then in December, you currently have $1.50. But if I get 50% of this, that means I get an additional 75 cents. Which means that we now have $2.25. So 50% semi-annually means like halfway through the year you're getting 50% of what's in your account. Well, 50% of $1 means to my dollar I'm adding an extra 50 cents. And now that amount is larger, so now it's $1.50. And on that $1.50 you're getting 75% of that. So you actually get a gain an extra quarter by having it compounded semi-annually instead of just at the end of the year. So what option's better will obviously be, even though it's $1, 25 cents, it still is a better option. So if you had $1,000, it'd probably be a good bit more than just the 25 cents. So as you work through the table here, the goal was essentially for you to take that dollar. So this little equation here is kind of set up for it that you have $1 or just the number 1, because it doesn't necessarily have to be $1. And what happens to that value if we plug in this little formula? So we're dividing 1 by a number of times, and then you're taking it to that same power. So you should have seen that as the values go on, they get bigger slightly. So this was 6. And you didn't have to carry out all the decimal places. So daily, remember there are 365 days in the year. So that would have been 2.71457. So you're still getting more because you're compounding the money more often. Hourly, how many hours were there?
8,760.
Yeah, 8,760 hours in a year. So that number would have been 2.718127. And then every minute, anybody know the song that goes along with it?
Oh, Nina started singing.
Oh, yeah, Nina knows it?
Nina, go.
From Rent?
Oh, we did the
Well,
Glee
we like the
version.
Glee version better.
Oh, well, of
I
course,
love
the Glee
her.
version,
Nina,
yes.
do it.
Nina, you did like
I
4
feel
times
really
already.
Oh, was she already singing it?
Oh, Pasha got it. Go, 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 go.
No. Okay, so there is a song that goes along with it, though.
Seasons of Love.
Oh my
But
gosh, that was like season
the goal is for you to kind of look at the last couple of values. What do you notice about the last 3 values? They're almost the same. And if we're talking about a dollar amount, it says what happens to the dollar value as you compound the interest more often. Well, you get more money, but, Cooper, you get more money, but what? At some point, the values stop increasing. So you're going to get more money, but like after the daily amount, these numbers are almost exactly the same. And if we're talking about money and we round to two decimal places, they are exactly the same. So for part 3, what happens to the dollar value as you compound the interest more often? Well, you get more money up until a certain point, because the more times you compound it doesn't necessarily mean that you're going to always get more money. So for number 4, it says, what do you think the maximum amount of money you can earn in a year? If you look at those last 3 and round them, they round to about 2.72. So the maximum amount that you're going to have is $2.72. Now, yeah, the decimal after it's going to change, but it's just changing in such a small amount that it's never really going to get more than the value of 2.72. So in your calculator, there is an E on your calculator, and if you take out your calculator, look at the left side of the right side of the calculator at the division bar. The division bar above it has an E. So if you hit the second division, and then hit enter, it calculates E for you.
That's crazy.
What do you notice about this E?
It's the same as the
It's,
number.
yeah, it's the same. So the value of E is 2.7182828.
Wait, wait, how does it know that though? Right?
It can read your mind.
That's what I'm saying.
I'm kidding. I when I think it.
Okay, so how does it know that? And if you like look at the backboard, you'll see that Jesse wrote.
Jesse Crowder?
Yes,
He was in my class
No,
last year.
Of course,
He-
Jesse
Of
Crowder.
of course. He wrote down the first, 20-some digits. There's a whole bunch.
Yeah, that sounds like a Jesse thing.
Yeah.
Why would
Okay.
it be a Jesse thing?
Because he's crazy. I don't know. He's crazy. He likes math a lot.
He's a crazy guy.
He's a little crazy.
Jesse's crazy.
Whoa, you're
So
calling him-
anyway, the number, this E, what other value do you know that we've talked about? A lot of geometry you would have talked about.
Pi?
Pi. So,
Wait, is E always that?
yes.
Oh.
So pi is always 3.14, blah, 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 blah,
1,
blah.
5, 2, 8, 3, 6, 7, 4, 7,
So, ladies and gentlemen, please, up here. So, pi is a value that you learned probably back in 5th or 6th grade to be 3.1415, blah, 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 blah. Generally, we know it is 3.14. E is the new number that you're learning this year. So, not only is there a pi that exists in math, but there's also a value for E. This is the value for E. It's always that number, just like pi is always 3.14. So if you flip the page, there's just a little bit, like a little paragraph at the top. So the history of math is marked by the discovery of special numbers. So pi was one of those numbers that was created way back in like the Pythagoras time, so like way long time ago. The imaginary number was also created. That's what the I stands for. So it doesn't stand for a physical value, but it stands for any negative underneath the square root. And now the number E would have been another value that was created. And it's called the natural base. So it actually has a name, like pi. I mean, that little character, somebody had to come up with that number, and that's pi. So the E, instead of really calling it E, we call it the natural base. The reason it's called the natural base is because it's always attached to an exponent. This guy here is the base. The base is anything that has an exponent attached to it. We've talked about exponential functions now growing when the base is bigger than 1 and decaying when the base is between 0 and 1. So now we're changing this base to always be, in this case, the value for E. So it's creating a new equation or like a third function for these exponential functions, and they call it the natural base. So a guy that found this, his name was Euler, he actually did a bunch of different things in math, but he lived from about 1707 to, it says 1783, and like back then, mathematicians, I mean that's pretty much when a lot of stuff in math was created. and they kind of worked on one thing until they found a pattern happening with that one thing. So he happened to notice that by taking this special formula and continuing to divide 1 by really large numbers, you end up still getting the same number over and over and over again. So he thought it was really cool, so then he showed another math guy, who showed another math guy, who showed another math guy, and they finally were like, yeah, you didn't come up with like some fluke, this is truly happening. So because he was the guy who created it, they gave it an E for his name, and now it's a number in math.
That's wild.
So you probably don't remember when you learned about pi, and you might not have been really told like all the behind the pi, the background behind the pi. But
I never watched it.
I read the book over this summer.
It's
It's
very
interesting.
long and makes
Yeah.
you like.
So this E, it says the natural base E is irrational, just like pi is irrational. It's just a number that goes on forever. You can never write it as a fraction. And yes, it looks like it initially repeats, but then eventually it kind of stops repeating. So it just goes on and on and on and on. That's what makes it irrational. So it says the way it was created by using this little formula, n approaches positive infinity. That just means this number is getting bigger and bigger and bigger and bigger and bigger. Like the 31 million, blah, 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 for every second there is in a year. Or we could even go larger and larger and larger. But it doesn't matter. The larger that value gets, it's still approximately 2.718, which generally when we refer to E, we use 3 decimals. So pi is 3.14. E usually is considered 2.718. With the rest of it, the repeating 281824 and blah, 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 blah. So now we have a new number to talk about instead of just always having pi.
It's crazy.
Questions on that? So it's like, at least you can kind of see like how it was created. I mean, you may not have ever thought of using that formula because who would, but somebody a long time ago did. But at least you know where the number comes from, where with pi, like you were too young to kind of give that big explanation, which we could probably do sometime.
We should.
Maybe in
Yeah,
trade.
can we?
That'd be a good thing to do in trade, because you'll use pi a lot in
Right
trade.
before Christmas time.
Okay, before Christmas time in trig?
Yeah.
I'll remember that for next year.
Okay. Wait, are you only teaching honors trade over here?
I honestly don't know.
Okay.
I have no clue.
You better be teaching numbers.
I don't know. I don't know what I'm teaching.
Gonna
I'm gonna be here, that's all I know.
Yeah, Julia.
Alright, so if you look at the problems underneath, we're just gonna do a couple of problems like the rest of this page for today. So if you're simplifying, it says simplify the following with the natural base expressions. What do you think you would do, Ethan? With e to the 6 times e to the cubed.
Something with their exponents. Also.
Yeah, what do you usually do with exponents?
Add them.
Add them. So that doesn't change just because we have an e sitting there. That's the same as having x to the 6 times x cubed, which would just be x to the 9th. So the property doesn't change just because we have this e sitting there. That e really represents 2.718, just like if it was a pi. So the second one says 18 e to the 6th divided by 2 e to the 4th. So Cooper, that would be
That would be 9 e to the second.
9 e to the 2nd.
Good job.
Divide your numbers, subtract the exponents. The third one, we have 4e to the 3x, and then that's squared. So Libby, what do you think you do with the squared?
You would put it to the other one, so the 2 would go to the 4, 16, or 6x.
Yeah, it becomes a 6x. So you multiply your exponents when you have a power outside the parentheses. So the 4 is just squared because there's really a 1 sitting there, 4 to the first, so now it's 4 squared. And then you're multiplying 3x times 2, so 16e to the 6x. So we're going to go back to the calculator because I'm going to show you another place where the e is also in the calculator.
Well, there's an EE, which stands for times 10.
There is that. If you look on the left side, so looking at the left side, like x squared above it is a square root, and then there's an log, and then underneath that says ln. Above ln is e with an exponent, and that's really how e is used. It's used as like the base of an exponential equation. So if you hit second ln, your e comes up already in an exponent form. And then if you type in the number -2, we can now evaluate e to the -2, which is 0.13533528832.
That's crazy.
Libby.
If you still did that, like, if you did.
You could still do the other one, you just have to use the caret button.
Okay.
Yep.
they still work?
They still work, yes. The other one still works, but this one already has it as an exponent. The second problem that you're asked to evaluate is e to the 0.3. So then you just plug in e with the exponent of 0.3, hit enter, and we have 1.3499 if you wanted to stop at like 4 decimal places. Or you could just say 1.35 because the 9 rounds 4 up. So that little e, the second with the ln, we'll use that one pretty often when you're talking about like exponents with that natural base. Any questions? So the last thing we're going to look at is to try and start seeing what the graph would look like. No, you can't graph these by hand, so you guys should be like, woohoo, excited about that. Yeah, exciting stuff, right? So can't do it by hand, we're going to have to rely on that calculator to help us graph it. But we will look at the graph. So it says the form for an exponential function is y equals ae, and then the exponent part is going to have a number with it. So there's an r with the x because that's the part that makes it either grow or decay. Because the base, the 2.718, isn't changing. And generally we say when that number is bigger than 0, it's supposed to grow, and when it's less than 0, bigger than 1, it's supposed to grow. In between 0 and 1, that's when it's supposed to decay. But that's always an e, which is always 2.718. So what makes it grow or decay is the number that's with the x. That, right, in this case, it's that 0.6. So if a is bigger than 0, which always has to happen, and r is greater than 0, then it is a growth function. So essentially, the number with x, if it's positive, it grows. The front number has to be positive for it to be a growth function, but it also has to be positive for it to be a decay function. So that a isn't changing. The negative part just like flex it, it just bumps it to go down instead of going up. So then the second part says, again, if a is bigger than 0, but r is less than 0, so the number with x is now negative, then it's an exponential decay function. So with the natural base equations, the part that makes it grow is whatever's attached to the power of x. So we're going to graph this with the calculator, but we're still going to make a t-chart. And you'll still use those same numbers. But it's more just having that t-chart there as like a visual to kind of know what the points represent. So in the calculator, where's my calculator? If you go to y equals, we're actually going to use the calculator to help us graph this. So you're going to type in the 2 first, and then the e with the exponent of 0.6. Don't forget the variable x. That's the part that makes it the equation so that we can graph for different values.
This is crazy.
So you can hit the graph button, and you'll see that it looks like an exponential growth function. You wouldn't know by looking at it that it has a base e just because it has that same curve of all the graphs that we've done the last couple of days. To actually graph it, to get the numbers, if you go second graph, there's a table of values for you to use.